Welcome, everyone. My name is Jack Moran. I'm a recent alum from Carleton College, and this project is kind of my senior thesis for statistics that I worked on all of last year. And a lot of the talks today were about things like earthquakes or solar flares or traffic stops. And my talk is not really that, it's about a method. And so today I'm going to share the lineup protocol with you and how we can use simulation to improve model diagnostics in binary logistic regression. So it sounds like a mouthful, but it's not so bad. We're briefly going to talk about motivation for why we might need simulation in statistics in the first place. And then I'm going to introduce the lineup protocol as a type of simulation. And then we'll talk about the study that I ran about logistic regression briefly at the end. So as far as motivation goes, I present to you all this QQ plot. And the question here is the sample normal? On the x-axis, we have the theoretical quantiles of a standard normal distribution. And on the y-axis, we have observed quantiles for a sample of 25 points. And so similar to the PP plot that was discussed earlier, if points lie on this 45-degree line, that is ideal for matching the distribution. So in this example, we see on the bottom left here that there are a couple points above the line. And so that would indicate a larger left tail. And so in our mind, for QQ plots with a lot of points, we have a really good visual of what it's supposed to look like. It's supposed to lie right on this line. But because there are so few points, we don't really know if this bottom left mishap is due to random variation or if it's actually the data is not normal. And so our mental image is breaking down because we're in this niche situation where we don't have many points. And so we can use simulation and just simulate samples also with 25 points that are from standard normal distributions. And then we don't have to rely on this mental image. We can just look at all the plots next to each other. And so that's exactly what's happening here. Plot 0 is the same plot we just looked at, and plots 1 through 19 are simulated from the standard normal distribution. And you can see when we look at plots like 2, 17, 13, and we know those are from a standard normal distribution, suddenly plot 0 doesn't look so bad as it did when we were just basing it off our mental image alone. And so we probably don't have enough evidence right now to say that plot 0 is not from a standard normal distribution. You'd have to not reject the null. And so this is a general problem. A lot of the times we don't have a good mental reference for some types of plots. And we as humans are really good at picking patterns out of randomness. And so those visual diagnostics are prone to overinterpretation. And so as a solution, we can simulate these references explicitly instead of having just a general mental image of what it's supposed to look like. And we can plot these side by side and really calibrate how we look at visual diagnostics. And so the lineup protocol is an example of a visual diagnostic that's used as simulation. So assume that we have a visual diagnostic for our observed data called the true plot. In the previous example, this would be plot 0, the thing that we're actually interested in. We're going to simulate multiple null data sets according to a null hypothesis and create null plots that mirror the true plot. So in the previous example, the null hypothesis was the data comes from a standard normal distribution. And so we create plots 1 through 19, where we know the data comes from a standard normal distribution. And then where it gets a little bit differently is instead of knowing which one the true plot is, we're going to randomly place the true plot among all of these null plots. And we try to pick the true plot out from the null plots. And the idea is if we are able to consistently pick out the true plot, then it must not follow the null hypothesis, because that's the only thing we've conditioned all of these null plots on. And so an example of this is we're going to use the same null and alternative hypotheses. And so this is a lineup. One of these plots is the true plot, and the other 19 are simulated to follow the null hypothesis. And so take a moment for yourself, look at all these plots and pick out the one that you think looks most different, or which one you would pick out of the crowd. Okay, so we got to keep it moving. So if you picked plot 13, you would be correct because plot 13 is the true plot. And the idea is if we as a group of independent observers consistently were picking plot 13 here, that would be evidence that 13 does not follow the null hypothesis. And 13 actually comes from a t distribution, not a standard normal. So it does not follow the null hypothesis. And as far as significance goes, there's a 1 in 20 chance that we pick the true plot at random. and that corresponds to a false positive rate of 0.05 or a p-value of 0.05. But that's with one person. And if we have many people, if we let small k of k observers choose the true plot, then the p-value is the probability that at least k viewers choose the true plot. And it follows this binomial distribution. So it's very easy to calculate. And as we increase the number of viewers, we get a more accurate p-value. So now, how can we take this concept of the lineup protocol and apply it to a common type of model, the logistic model? A quick recap, logistic regression models binary data. So that's yes, no, success, failure data. And we take these continuous predictors here on the right. We use the inverse logit function to take them from this interval of -infinity to infinity, and we transform it to 0 to 1. And then we interpret that number 0 to 1 as a probability of success. And we assume only two things of our data. The first is independent observations. Knowing the outcome of one observation doesn't give us any information about the outcome of another. And two, log odds linearity. And that comes from the inverse logit function. And so that's a very quick recap. We're not going to get super into it. But in practice, this is how the lineup protocol would work. We have some raw data. Here, we're modeling success failure as a function of score. It looks like as score increases, success also increases, but we don't have that many points at high values of score. And so maybe it's a little unclear what the relationship is. We fit a logistic model, and this is just the summary from that model. We see that score is a significant predictor of success, but the question is, does the data follow all the assumptions of logistic regression? And so remember, the first step in a lineup is we need to make a visual diagnostic. And so this is a bin residual plot, which is just a very common diagnostic for logistic regression. And this part looks okay on the left, but on the right here, we see the outliers. And so normally this is a red flag. But remember, we didn't have that many points for high values of score. And so you could ask yourself, maybe is this like the QQ plot? Maybe is this random variation and we just didn't have that many points? And so we can use a lineup protocol to kind of answer this question. And so this is a lineup of that same situation. All of the other 19 plots, except for the true plot, are simulated from the logistic model. And it's kind of cheating because you guys already saw the real one. But actually, I ran a study kind of testing the lineup protocol in logistic regression. And this is one of the lineups that we gave to participants. And so the true plot is in plot 1. It was chosen by 7 of 29 participants, and that corresponds to a p-value of 0.0046. So we would reject the null hypothesis that the true data comes from or follows all of the assumptions of logistic regression in favor of the alternative that the data is violating either independence or linearity. And so steps from here, if you were fitting a model, is you might consider variable transformations. You might look for some underlying group structure and trying to account for that. But as of now, your data is not appropriate to fit a logistic model on. And so I ran this study for logistic regression, testing the lineup protocol. The basic idea was we're going to simulate data so we know exactly how it's violating the assumptions of logistic regression. So we had 3 groups: a control group where the data was good and there should have been no issues, a log odds linearity group where the underlying data successes has a quadratic term that's omitted from the model, and then also independence violations where the underlying data is binned into little groups, and then those groups each have random effects that increases or decreases the probability of success. And so we have these 3 different violation types. We're going to use 3 different types of diagnostic plots paired with those violation types. We have bin residuals with a 95% error bound, and empirical logit or log odds plots. And so we're going to pair these different violations with these different plots. We're going to make lineups, and then we're going to pay people on the internet to evaluate these lineups, or just with the prompt like I gave you guys, which one is the most different. They'll give their answers and their reasons, and then we can evaluate for a p-value for all those lineups. And the questions we were trying to answer is, when is the lineup protocol better than other quantitative diagnostics or diagnostics that also return a p-value, and what type of diagnostic plots are most effective for use in the lineup? And so quick results, Comparison to other quantitative diagnostics, the goodness of fit is another diagnostic for general model fit. And so you can't use exactly what we think of when we say goodness of fit, but this is a slight alteration on a classic goodness of fit. And so the lineup protocol had many more false positives than the goodness of fit. So there was a high type 1 error. Compared to the goodness of fit, the lineup protocol performed worse at detecting linearity violations in data, but it performed better than the goodness of fit test at detecting independence violations in data. And so that's how it compares to quantitative diagnostics. As far as plot type goes, all plot types had pretty high false positive rates. The bin residual plots performed better than empirical logit plots at detecting linearity violations, and all of the plots had similar power in detecting independence violations. So that's a very brief overview of the study. Conclusions is that quantitative diagnostics, they both have unique strengths. Best practice, if we're trying to evaluate logistic data, we should use both the lineup protocol and the goodness of fit test. And then if we're using a lineup, we prefer bin residual plots over empirical logit plots. And so that when we're fitting a model and we're doing logistic regression, these are things to keep in mind. And as far as future direction goes, we saw that the lineup protocol was effective at detecting model violations with independence violations. So it'd be nice to further explore how different types of independence violations work with the lineup protocol and kind of look at it like a mild to severe, how powerful is the lineup protocol. There was also, lineup protocol had a huge type 1 error rate. And so that's a big problem moving forward, and it'd be good to look into why was it so high and what do you to minimize that type 1 error rate. And finally, instead of using bin residuals and empirical logit plots, we could also consider a raw bin data set as a plot type, because you can use the lineup protocol with any visual diagnostic. It doesn't have to be specifically like a residual plot or something like that. So yeah, thank you guys. That's a very brief overview of what I did. A big thank you to my statistics faculty at Carleton. They were very supportive and made the whole project super fun. And yeah, thank you guys. I think we have some time for questions before the next talk, so I'll stick around. Thank you all.